I know a lot of you guys are not able to make class on Tuesday, so I figured it'd be a good idea to actually just have this PowerPoint sort of give an explanation over what's going to be covered on this PowerPoint because this PowerPoint does have a lot of different topics that might be a little confusing at first to some of you. So I figured it'd be a good idea to at least make a video of me sort of going over the PowerPoint, kind of like I normally do in class. And that way, at least you guys can get some background information before doing the lab. And if you have any questions, obviously when you're doing the lab assignment, you can send them to me or email them to me, um, and I'll try to get back to you as soon as I can. It's during the Thanksgiving break, so there's no guarantee you get a quick reply, but I'll try my best. Um, and Like I said, the lab would be due next Tuesday, so just turn it in to me next Tuesday. And All right, so with that, let's begin. So, all right. All right, so I'm not sure if it's all recording on the screen, but the topic of this discussion is going to be waves, currents, and tides. So, let's see. All right, for the most part, it's all right. These are just some of the objectives. Obviously, you want to sort of understand what sort of system or environment you need to be in to create these waves and currents. And so this sort of plays a part to what sort of setting would give you these sorts of waves, which also would as well give you currents. So basically, we're trying to go over the sort of breakdown of what a wave is and how it affects the motion of water, essentially, when you've got a wave. So that involves calculating velocity, wavelength, wave period of deep water waves, which is important because deep water waves and surface water waves have a very interesting distinction, which has to do with how how far the wavelength is of them from the seafloor, which is basically half of the wavelength. So there's sort of an inverse relationship between the wavelength, which I'll go over that, and sort of the depth of the seafloor. And so we also want to understand what causes waves to break and form. So why do we get these sorts of depositional environments like a barrier island? You've got sand being deposited, and then you've got at the same time you've got sand being eroded and weathered. And so if you go to Miami Beach, you see these things called jetties, which essentially they're sorts of barricades to prevent this thing called longshore drift erosion. Because if we didn't have these jetties, we would have most of the sands being eroded away from different parts of the barrier island. So it's essential to understand these sorts of processes before we go into detail about what we can do about them. And this is also going to identify major surface ocean currents. So the Gulf Stream, for instance, is one of them. And then also characteristics of principal deep water currents. So sort of a relationship between what deep water currents are and how these are sort of affected by different processes, mainly temperature, salinity, which affect density. And that's what mainly drives these currents. They're density driven. And so, erosional and depositional features along shorelines. So, we can talk about stuff, like cliffs, which are erosional features, or just a barrier island with sand being deposited, and discussing the causes of tides and distinguishing among different types of tides. So, we obviously understand that tides it's sort of a basic understanding would be that the sea level rises and falls throughout a period of time, which is related to gravitational attraction between, for the most part, between the Earth, Moon, and Sun system. And basically, how this can affect the water, or sorry, the sea level, and how frequently do we get these sorts of settings. So, going into waves, for the most part, most of the ocean waves are pretty much derived from wind. Wind is sort of the main form that sort of creates a lot of these systems. And so there's sort of
if you dissect the wave and you look at it, you have a couple different key components. So you've got the crest, which is essentially the apex or the top of the wave. You've got the trough, which is sort of the low point of the wave. You've got this thing called the wavelength, which is basically the horizontal distance between one crest and another crest. So if I were to measure with a ruler from one crest to another crest, that's a wavelength. And the wave height is pretty much, if I took the difference in height between the trough and the crest, that's my wave height. And the base is just the depth of water circulation. So below these waves, you've got water particles that are rotating in a gyre, and they're sort of circulating, and those sorts of also drives these wave characteristics as well. And so the base is just the depth at which the end of wave circulation of these water particles exists. So below the base, you don't have those water particles moving in that gyre, but above the base, they do. And so this is sort of showing as you've got a wave approaching the shore. And so you start off, you're in an open ocean, so you've got waves, just constant wavelength just flowing. You've got the particles moving. And you see below on the lower left, depth is greater than 1/2 wavelength. Now what does that mean? So there's sort of a correlation that has been identified between the wavelength between two crests of a wave and the depth to the seafloor. And as you guys notice, as you get closer to shore, obviously the depth to the seafloor decreases because now you're getting a more shallower water set. So as a result, there's less distance between the top of the wave and the seafloor, and you see that your wavelength now between the two crests starts to shrink. So as your depth to bottom decreases, your wavelength also decreases. And as a result, your velocity decreases now, because now you're kind of smushing the waves together so they slow down, because now you don't have that big of a depth where they can flow really quickly. Now they're slowing down. But inversely, now your wave height increases. So when you shrink the wavelength and you slow down the velocity and the depth to seafloor decreases, now you increase the wave height. So people talk about, for example, when you picture tsunami, although it's not really always the case, you think of sort of a 100-foot wave, or most of the time it's just a mega siege. But for the most part, in the open ocean, when they've tracked tsunamis, what they've noticed is that they move extremely fast in the open ocean. But you can't see them because in the open ocean, you've got such a long depth that your wave height doesn't really go up that much, and you have very fast velocity. But as soon as you get to shore and your velocity decreases and your wavelength decreases and your depth to the bottom also decreases, your wave height just exponentially goes up, and that's when you see it. So you don't see it until the very end. And so this is just sort of the relationship that's between the wavelength and the wave height. And again, once you hit this sort of, when the wave sort of crashes, we call it a wave break, and this is sort of the surf zone. So you guys can tell if you surf, obviously you're going to be in this sort of environment. And the relationship mainly is between these deep water waves with the velocity, wavelength, and also wave period, with just it's related as a number of waves per time that you see. This is sort of the relationship, and basically a deep water wave, as opposed to a surface water wave, is basically considered where the water depth is greater than half the wavelength. So if we go back to this image here, you see that the wavelength here is a considerable amount, but here it gets smaller, and the water depth obviously is small as well. So only in these deep ocean waves where we see on the left corner where it says depth is greater than half the wavelength, we call that a deep water wave, where everything else we call a shallow water wave. And so there's also this thing called longshore transport. And so when you think about, let's say, picture in your head Miami Beach, for example. You've got a lot of shoreline erosion and deposition going on. So if you take a look at the sort of diagram here, you're going to see that basically you've got this longshore current that's picking up sediment, moving it, and then transporting it elsewhere. and sort of moves in a zigzag pattern. So it doesn't always move straight. It moves in a zigzag pattern, and usually it moves in one direction. So a lot of times you notice you go in the water at the beach, you think you're just stationary, you're just sitting there, not moving, and then all of a sudden you look up and you notice that the umbrella that you had, the towel that you had on shore, has magically moved to the left. Except it hasn't moved at all. You've just moved to the right because the longshore transport currents are moving you, even though it doesn't feel like they are. So slowly, you this sort of current does the same thing to sediment, but on a much sort of broader scale. So you get these sort of different depositional environments called spits and baymouth bars, which are basically deposition of the sediment that's being moved, and you also get erosion of the shoreline. And so this can cause a lot of coastal erosion problems in a lot of areas. California is one of them, but mostly it's the East Coast that gets them because you've got these barrier island systems that are just sort of susceptible to this. So you have to bring in a bunch of sediment from other places and deposit them and just try to combat this. You can't really do anything to fix it. You've got levees and jetties, which I mentioned earlier, but those things can't really prevent this entirely, this longshore drift system. And so this is two main types of shorelines. So we have two types of coasts. You got emergent coasts and submergent coasts. I tend to think of them as active versus passive coasts because in emergent coasts, you see these cliffs and terraces. So the first thing I think of is that the whole entire surface has been eroded just by these waves that have just eroded and carved their way through the rock. So you've got all these cliffs, and it's a very active shoreline. So along active margins, you're going to sort of see these emergent coasts. Whereas if you look at the barrier islands, it's sort of just mainly sand that's been deposited and eroded. And this is sort of along these passive margins, so along like the east coast. Okay, now we're going to talk about currents. So basically currents, again, wind is sort of the dominant feature, but now you've got water density and temperature, which also affects them as well. All right, so we've got surface ocean currents. Let's keep this going. Okay, so when you got surface ocean currents, basically you've got wind that's creating this movement of water, and you got this thing called the Coriolis effect. And so the Coriolis effect is influenced by the rotation of the Earth. And what happens is that it actually deflects moving surface currents. So if you got an oceanic surface current where that's moving north, for example, if you're in the northern hemisphere, the Coriolis effect, because of this rotation of the Earth, is going to move it right. Whereas if you're in the southern hemisphere, it's going to move left. So if you ever try to flush a toilet in the northern hemisphere, you're going to sort of see it make like a clockwise motion, whereas in the southern hemisphere, it's going to go the other way around. And there's this sort of feature that goes on where you've got warm currents moving from tropics to poles, and you've got cold water currents moving from the poles to the tropics. This is sort of this exchange of warm and cold currents. And basically you've got heat that's being redistributed throughout the entire ocean, which really plays a role in climate. And so this is an example of the Gulf Stream right here. So you've got sort of these cold currents moving from the poles. This is the Southern Ocean right here. And it's moving to the sort of tropics area, and then it turns into this warm ocean current, which then goes back to the poles. And so this sort of relates to deep water ocean circulation. And this is mainly driven by density. And so apparently when you've got two types of ocean currents that have different salinities, which is just the total number of dissolved salt in there, and temperature, you sort of got this thing called subduction, but it's called ocean current subduction, which is when you've got one current goes under the other one because it's more dense. It's kind of like if you try to put oil in water. One of them is more dense, so it sinks under. And as a result, you've got cold seawater with high salinity being the most densest. So you got this deep water circulation, basically, where you've got this cold, high salinity water in the poles, which is super dense, and it sort of travels to the tropics, and then it rises up again, and then essentially it repeats the cycle. Then it becomes more cold, goes back down, and when it warms up, it goes up again. So there's sort of this relationship, we call it the oceanic conveyor belt, where you've got different water currents of deep water currents of different densities as a result of different temperatures and different salinities that sort of influence the climate. And lastly, we're going to talk about tides. So as you guys think of them, you've got periodic rhythmic rising and falling of water along coastlines, basically to that gravitational tug of the sun and moon affecting the earth. And so most oceanic coastlines experience 2 high tides and 2 low tides each day. We call this a semi-diurnal tide. If you get 1 coastal high and 1 coastal low, it's just a diurnal tide, but most of them in general, Florida too, are semi-diurnal tides. So you've got 2 times during the day where you got high tide and 2 times during the day where you have low tide. And so on top of this, we get these sort of settings which sort of relate to the positioning of the Earth relative to the moon and the sun. And if you have them all in a perfect alignment, you get what's called a spring tide, which basically means that your low tides are going to be lower than normal. So they won't be as high up. But now your high tides are going to be higher than normal. And so this can cause problems. You can get a lot of flooding during spring tides, and this is when most of the damage is done related with flooding. And then you get neap tides. So basically, when you've got the moon, the earth, and the sun kind of at a 90-degree angle to each other, you get lower high tides, so your high tides aren't as strong, but now your low tides are a little bit higher than normal. And so here's just an example. This is, the Bay of Fundy, which is a very interesting place off the coast of Nova Scotia, Canada. And as you guys can see, there's sort of 2 photos taken at different times, which show low tide versus high tide. So you see there's a ship right here that's sort of buried in this tidal mudflat and in low tide. And then as soon as it's high tide, you see it just rises up because of the water level just goes back up. So you don't want to be caught in this area, riding on a boat halfway out, and all of a sudden it goes to low tide, and then you're just stuck in the mud. So it's pretty interesting how this sort of works on some areas. Obviously here it's a lot more exaggerated than ever else on the planet, but it's a good example. And so here's the assignment. It seems like a lot. I haven't looked too much into the book. Obviously I'm going to look into it tomorrow on Tuesday. And if there is a section that I tell you guys not to do, I'll send out an announcement over it. But so here is the assignment, and like I said, you guys can turn it into me next week. If you have any questions, just send me an email. I'll try to, as best as I can, to reply as quick as I can. But again, it's during the Thanksgiving holiday break, so I might be sort of not present during Thanksgiving to send back a reply. But I'll try my best anyways. And yeah, guys, if you have any more questions, please send me an email. And someone also sent an email to me regarding mastering geology. I believe there was a no pre-lab or something. I'm going to look at that and see what's going on in the system. And I will send out a message regarding it as well. So thanks for sticking around, guys. It's a very info-packed PowerPoint, and I felt it was good that I, gave a PowerPoint lesson to you guys, because it's a lot of stuff to take in at once, especially when you get these currents and waves and tides, and even at times I tend to struggle with these. So I really think that it's good that I go over this so you guys can at least get some background information instead of not getting it and then struggling on the lab and not doing well. So that's why I thought it'd be good to give this. So yeah, guys, I will see you next Tuesday, and have a good break, guys.